Okay, so last year in our organization we ran a survey, a quantum open source survey, and we asked basically all the quantum practitioners what language. We asked many questions. The 31st question was like, what language do you use to develop quantum software? And as you can see, 95% of people replied it's Python. And yeah, you can see the full stats on the website there. And we have been running this survey for like 4 or 5 years, so we also track trends. And you can see there is some interesting trend if we compare with 2022, which is Python is still up there, 90, in fact, is increasing by 1%. But what's emerging is languages like Rust, which 2022 was used by 7% of practitioners, and now it's used by like 13%. So, and in fact, the next question was, which language would you like to learn? And it's most promising for future use, again, in the context of developing quantum software. And the answer for the first year was that Python was not the first one, but Rust overcome Python. And that's, you know, for a Python audience, something to be worried about. So the topic of this talk is like, can we do something to sort of invert this trend and keep doing quantum software without leaving Python behind? And that's also a selfish goal because I don't want to learn another language. I want to focus on like my quantum research stuff. I'm sure Rust is great. I was at Luca Palmieri's workshop this morning. But I still want to keep focusing on, you know, my quantum stuff and do things in Python. So let's see if that's possible in the future. So to set up the scene of this talk, I'm going to give an introduction to quantum computing in, I promise, in 2 slides. You don't need to know any quantum physics. I don't know any quantum physics myself, even though I've been in the field for a long time. I'll go through the quantum software stack. I'll explain the role of Python in the current stack. Why do we need speed for classical computer in the quantum stack? And I will use 3 case studies, a simulator, you will understand what that is, a transpiler, and a compilation engine, where this trend is visible. So they are sort of shifting to more like native and performance languages, sort of leaving Python behind. So quantum computing in 2 slides, it's ambitious, but I will try. So quantum computing is a paradigm that uses properties of quantum mechanics. Superposition, entanglement, and interference are the most important to improve what we can do in terms of speed and security with computers. It's been an area of research for 20 years. Been involved in that for like maybe 10 years. And hopefully feasibility is coming in 20 years. It's obviously hard to predict. I just put it there because usually it's one of the frequently asked questions. So where are we now? We are in something that people call the NISQ area. So we are at intermediate scale, so around 100 to 1,000 qubits that we can engineer and they can perform. But they are still noisy qubits, so we cannot really do many things with them. It's still an incredibly interesting area in terms of research, and we do want to scale to not having noise and many more qubits. So the application, obviously, the most famous is that if we actually implement quantum computer, we can break RSA. So we can break some protocol of cryptography as we use them now. But what is probably more interesting, because it needs less scale, is that we can simulate a quantum system, which is something that would take lots of time and lots of processing, time and energy to do it with classical computer. And simulating quantum system is really useful because if we have that, we can do things like more efficient fertilizer, which is good for agriculture, I guess, or new drugs, like pharmaceutical drugs, and like new materials and things like that. So things that are extremely important. I don't understand many of these applications, but even from the title, you can understand they are very important. And we can do, in a slightly more efficient way, also things that we already do with classical computer, like routing and scheduling. So more from an algorithmic point of view, what we want is to have a quantum computer. That's sort of the end goal, is to have a quantum computer that can solve a problem that we care about. So it's not like a made-up problem just for research. Perhaps one of the problems I was talking about earlier, that we can solve faster, or if you prefer some other metrics, cheaper than with a classical counterpart. So, and from the algorithmic point of view, we made great progress in the last 20 years. We have an algorithm that can do unstructured search, so you have n items and you need to look for one. The best we can do classical is like linear, but we can do square root of n in the case of quantum algorithms. We can do factoring, which is at the base of the RSA protocol and cryptographic protocol I was speaking about, where the best classical is sub-exponential on the logarithmic of the number you want to factor. So just maybe you can look at it as the logarithmic is like the number of digits of the number, and the best algorithm is sub-exponential in terms of that. But it turns out in quantum, because of Shor's algorithm, probably the most famous quantum algorithm, we can do this in polynomial time in the number of digits of the number. And that was the biggest breakthrough for quantum algorithm research. To simulate quantum physics, here the equations are more complicated, but again, the improvements is sort of exponential. So what you can simulate now, a physics system that you can simulate in exponential time, you will be able to simulate it in quantum polynomial time. So that's all nice, but it obviously assumes you do have a quantum computer, which at the moment is not yet the case at a large scale. But anyway, hopefully you were already somehow familiar with quantum computer, and this just gave you a recap. In fact, the news of this week is that the threshold for the number of qubits that we need to break RSA was improved to be less than 1 million. The paper is still under review, but that's, as I said before, we are around 100, 1,000. 1 million sounds very far away, but in my opinion, achievable. Yeah, we will save the question for later on, like, what happens if we break RSA, because that's not much the topic of the talk. So that's all nice from a research and algorithmic point of view, but if you are just like a software engineer and developer, you probably don't really understand what you can do right now with quantum software. So I'm going to go through a typical workflow of a quantum computer developer. So first of all, you either develop an algorithm or you speak with a friend who is an algorithmist in your research group. And what they will do is come up with something that looks like this. So it's basically, if in classical computer science you studied like Boolean circuits, this is sort of similar. But instead of like AND OR gates, you have some different kind of gates. And instead of like bits on the left as input, you have qubits. And then at the very end, you have this concept of measurement, which is basically observing the states. But the point is that this is really something that you do on like pen and paper. You like solve some equation, you prove a theorem. If you are sure these circuits will help you break quantum cryptography, but otherwise it will just stay in a paper. So next, you can actually code this up. So if you have a circuit like this that you find in a paper, you can actually install something like Qiskit, which is a library in Python by IBM. And you can define things in Python, the same things that are drawn there in the circuit. So you can say, OK, I have 10 qubits. I want to build a circuit which has 10 qubits. For each circuit, I want to apply this gate on the qubit I, which is sort of what we are doing here, assuming these were like 10 qubits. Then you do other things here. You apply some gates, and then you measure them all. So there is sort of an API to do whatever you do on paper to define circuits. And once you define the circuits, you really define a quantum program. So you have this Python software. So this is the Qiskit symbol right here. And let's say now you want to run on an Amazon bracket device. So it turns out that AWS also has quantum computer that you can access on the cloud, and you can dispatch jobs that are written in Qiskit in this Python toolkit. So what you do is, you pip install some library that is called Qiskit bracket something, and then you import this, and then you instantiate the backend, which in this case, you notice it's local, which means it's just really running on your machine, but it's a simulation of what would happen on the quantum computer, and you run it. And this is really to simulate that you are doing the right thing. Obviously, as we were saying before, this will take lots of time on your laptop, especially when the number of qubits increases. So it's really just to proof check that you are doing the right thing on small inputs. Next step, as a quantum developer, you say, OK, this is running fine on my laptop. Let me try on another simulator, but this time on the cloud. So it turns out that Amazon are actually some machines that are classical machines, but that can simulate exactly what a quantum stack would do. The machine is called DM1, and you can actually instantiate that. You can, same story. You get the backend, you run the circuits, you get some result back, and you say, OK, this is running fine on the classical simulator on the cloud as well. So now you really are confident enough that you can spend money on the quantum hardware, which unfortunately right now is still quite expensive. So every time you run a job, it will cost you much more than, let's say, an EC2 instance on AWS. But now you're confident because you trusted your algorithmic friend, you are good at writing Python, you simulated on small input, you simulated the cloud, the jobs are dispatched to the cloud perfectly. So now you can run it to an actual hardware. And this is from the point of view of sort of the user developer that just want to run things on a machine. But in this talk, we are going to see what happens actually behind the scene when something is run on a hardware, or rather on a cloud computer stack, which can be Amazon bracket, it can be a Google stack, it can be an IBM stack, and every company that owns a quantum computer. So this is the stack. So something important to notice here is that as opposed to classical computer, where most of us, I guess, we were born when most of the stack was already there. So we just went to uni and we learned Python. We maybe learned some assembly, at least I did in undergrad. But we didn't learn things like, at least I didn't learn things like error correction and how to do it in how to manipulate bits so that they are encoded and they are, that the computer runs without error. You never cared about things like that. It turns out in quantum, we are at the stage where we need to care about those things. And it's actually, in my opinion, really interesting and really exciting because we have the opportunity to learn from classical computer and reformulate completely the stack from the ground. So what you see here is a real picture of a machine of IBM. The quantum chip is somewhere here. I don't really know. As I said, I don't understand engineering, like mechanical, electrical, or physics. But as far as I understand, all of this is a fridge to bring things down to very low temperature, because that's how superconducting work well. So let's say we don't care about this stuff here because we are mostly computer scientists. But right on top of that, we need to write some firmware. And some firmware that will allow us to go from what we wrote in Python to things that are closer to machine level, which are things like pulses. So you actually have like laser pointing at superconducting material things, and that will simulate whatever you want to do on a qubit. So let's say you want to apply a NOT gate. When you have like a 0 qubit and you want to flip it, that's called the NOT gate. So you do that by actually shooting some laser against something. So it's a very physical thing. They are called pulses. And you need a firmware to control these, and the firmware is actually classical. So the nature of the thing that will happen after you shoot the laser against the material is quantum, but the way you control these pulses are classical. So this is the bottom of the firmware, but let's go back to the top, which is the algorithm that our friend provided. So let's say we start from there. This is exactly, I think, the same circuits as before. So we did write it in Qiskit, so now it's in Python. We don't need to, parse a PDF with a picture here. So we have it in Python, and now we can compile it back. So compiling in quantum is a bit an overloaded term, because it means both going from a high-level language to the low-level language of pulses, but it also means something else, like we will see it later in one of the case studies that not all the devices support all the gates that you can specify logically, so you will have to do some optimization there. And as I say, there is a full stack of like controlling the errors so that you can reduce the noise of the computer. So what is important is that all of this stack is really classical software that runs with like classical languages like Python. And only at the very end you have physics and like quantum mechanics that acts upon the qubits. And in fact, in the example we were saying before of development workflow, what you want to do is simulate even the physics part. So often you want to build a classical simulator because you want to be confident that what you will be doing, the money you will be spending on a quantum hardware is actually worth. So what is the role of Python in this stack? So it actually has a big role currently, as you said. In the survey, 95% of people are still using Python. And that's because we have many domain-specific language or embedded domain-specific languages that are written in Python, and thanks to which you can write quantum algorithms. Things like, this is probably the things you have heard of, is Google Circ is an example, IBM Qiskit, which we used for our code snippet before. There are other smaller companies like Rigetis, PyQuil is one of them, and so on. So defining a quantum program is something you can already do in Python. The choice of Python is because we already have libraries. This is mostly a research field. There is lots of hype, in newspaper and things, forcing it not to be a research field, but effectively it's still a research field. So most of the people working on it are still scientists, are people like mathematicians, physicists, and these people mostly like Python. So they have access to lots of tooling, lots of libraries like NumPy, SciPy, Matplotlib, and all of these are in Python, so we want to reuse those. So at the level of front end, we are sort of set on Python already. we do want to do rapid prototyping of these algorithms. So we use things like Jupyter Notebook, same as like you want to do a rapid prototyping or like of data science or machine learning stuff. And in fact, we are using the same proven pattern that we already use in machine learning. So we have a Python front end. But what is emerging now is that things that are below the front end in the stack are written in like more performant languages like C++, or they use libraries like NVIDIA CUDA, for efficiency mostly. And something that is also very important is that we are at the research level, but we are also at the point where we are learning and teaching quantum a lot more than actually solving practical things with. And this is really important to, raise a generation, assuming there will be another generation of people that people will work on quantum and hopefully build a quantum computer. So yeah, and education, as you know better than me, probably Python has been so far the most successful language for that. So, and the next question is like, why do we need speed in this stack? So that's because when you are prototyping, you do need very quick feedback. You want to type an algorithm. Again, this is the same in classical or quantum. You want the results to come back to you in a very short time. What is also interesting is that we are writing algorithms that are sort of like a ping pong between QPU, which is the quantum processing unit, and CPU. So there are so-called hybrid algorithms where some computation happens on actual classical clusters or high-performance computers, and then you send the results to the quantum machine, and then the results comes back. You do some post-processing. You send back the input, and so on. And this is really important in things like error mitigation, which is one of these components I was showing before. I was showing before that allow to correct the noise on the machine. Something to keep in mind is that the scale here, once you want to simulate a quantum algorithm into a classical computer, the scale goes again exponential. So you can take a qubit and in a very naive way map it to a vector, something that we will see later. But if you keep doing this for 50 qubits, you will already have something that is like 16 petabytes of data. So at that point, if we want to simulate things before running on a machine, we need high efficient classical software to do that. And finally, at the very end of the stack, we need to control this physics phenomena that happen with certain clock. And we want to catch up with this clock in an efficient way. So the firmware that controls these pulses I was showing to you before, the firmware needs to be as efficient and with the same clock as the phenomenon that happened there. So you want something that performs really well and fast. So because of this need for speed, it turns out that many people are keeping Python for the front end, but they are dropping it for things that are so-called the hot loops, where you need more performance. Things like simulation, like transpiling, like the firmware control. And I'm going to show you 3 case studies where this happens. I picked these 3 case studies because my work has intersected into those in the last year. So the first case study is something called Crack. It's developed by ourselves, the Unitary Foundation, and it's a quantum circuit simulator. So you can run it on your laptop, and it's open source, and you can, as input, take Qiskit circuits, the same one that you dispatch to quantum hardware, but you can actually simulate with and without noise on your computer. And the way you can imagine simulation in quantum is you take 1 qubit, And you can express it in the form of, if you know a bit of linear algebra, this is just like a vector. Let's say the qubit 0, you can express it as a vector of 1 and 0. The qubit 1, you express it as a vector of 0 and 1. And the superposition of qubit 0 and qubit 1, you can express it as like alpha and beta in a vector. And any transformation, like the NOT gate I was talking before, the one that flips a qubit, you can express it as a matrix. So you can understand that once you scale this to multiple qubits, from 1 qubits, now you have 2 complex numbers. In this case, they are integers, but in general, they are complex numbers if you have like alpha and beta. Let's say you have 2 qubits now, then you take the tensor product of these and another qubit, so the size of this vector becomes 4. And then it becomes 8 and so on. It scales exponential. So what you will have to run on your classical machine is basically matrix vector multiplication with huge matrices and huge vectors. And in fact, if you have a number of gates in the circuits, so the squares that you were seeing in this picture before is G, and the number of qubits is N. The runtime is of the algorithm, the naive algorithm to simulate is something like G times 2 to the N. And there is not much we can do better than this, obviously, because otherwise we wouldn't need a quantum computer at all. So they are basically classical linear algebra tasks that we sort of already learned how to do with GPUs, because we are using them in like machine learning already, and like video games or like 3D graphics. So fortunately, we know how to do them faster. Not incredibly fast, but we know how to do them more in parallel. So the requirement is something similar what GPU is good for. There are other simulation techniques that are more complex, but as I said, they are not extremely more efficient than that. And in particular, one of the requirements of our simulator is that we want it to be used for things like education, or to be used even on your browser. We have some like web assembly way of running it. So we are really stressing on portability so that many people can use it. So that's another requirement. And we want to accept circuits written in any of these front-end languages that I was talking before. So let it be Qiskit, Circ, or like Penny Lane. We accept all of those. So the way we are doing it is we wrote the core in C++ 11. This is mostly work by my colleague Dan Strano. And it's basically an external dependency-free package when it comes to CPU. And if you want to use GPU to accelerate the simulation, you can use the OpenCL libraries. And then we just have a wrapper around it, binded with C-type to C++. And that allows us to use Python as a user of the simulator, but all the speed and the need for speed I was talking about before happens in C++. So this is an example of performance. You have like 17 seconds to run at 27 qubits. This is one of the algorithms that is used for cryptography. And this is where you can run it. It doesn't scale much more than that. You can wait for maybe 1 hour to have like something like 30, 35 qubits, but then it becomes very, very intensive. But still, thanks to C++ or the performance with C++, we can get some very good number for a good number of qubits, pretty similar to the number of qubits that we would have on quantum hardware anyway. So another case study is a transpiler by IBM. It's part of the Qiskit toolkit. And what is a transpiler in general? So the problem it solves is like, we have these circuits, we have these algorithms, and now we want to run them on hardware, quantum hardware. It turns out that the physical devices, because of engineering limitation, have lots of constraints. So the gate set is not the same that you don't have the same freedom that you have in when you write the circuits on pen and paper or in like matrices. Because of engineering limitation, they only implement certain gates. So that's limited. The connectivity is limited. So this is a real example of a connectivity graph of IBM Q Yorktown. I think it's a decommissioned machine. It used to have 5 qubits, but for example, qubit 0 and qubit 4, or qubit 1 and qubit 3 were not connected directly. So you couldn't put a gate directly there. And in general, maybe one takeaway is that hardware is really noisy in quantum. So let's say you have a logical circuits like that, where you use X gate, use H gate. Again, you don't really need to know what they are, just think they are like AND or NOT gates. But you do understand that there needs to be between 1 qubits and one other. And for example, if the algorithm was written like this, there would be a connection between qubit 1 and qubit 3, but the connection in the hardware doesn't exist. So the first thing you want to do is transpile these circuits to a circuit that, first of all, matches with the gate set of the hardware, but also with the topology of the hardware. So you don't have any more connection between 1 and 3, but you have only connection between 0 and 1, for which we have an edge for between 1 and 2, and so on. So you can see the size of the circuits is slightly larger now. The gates are different, but logically, the circuits is doing the same thing. So if you calculate the metrics that correspond to the circuits, and you calculate this one, they are exactly the same thing. So in fact, this is not even a problem with metrics. You can see it as a problem with graph. So given a graph like that with some nodes and some edges, can I map a graph to this topology? So this is a classical problem that has application in quantum computing, and that we want to solve really fast because these circuits we don't want them to blow up, and we want to solve them really efficiently in a way that the output circuits is as efficient as the one that was written logically, otherwise we lose the computational gain that we gained in terms of algorithmic time. So this is a case study where the problem is really, classical, and the IBM team was struggling to get good performance with Python. So about in 2022, so 3 years ago, they decided to rewrite the package that does transpilation in Rust. And that's because of the thing Rust is famous for. You can do things in parallel in a safer way, and yet you have the portability and the platform support that maybe you don't have as easily in C or C++. So another advantage of Rust is that you can still package it in Python, so you can still reuse the Qiskit ecosystem. And the way they achieved it is actually through these PyO3 bindings that Luca was talking about this morning. So what they achieved, you can see all the results in this repository, where they also have a framework to benchmark these transpilation tasks. By going between version 1.2 and version 1.3, the API didn't change of this transpilation. The feature didn't change. Well, maybe some feature did change because they did upgrade the major version, but the minor version. But what they achieved is actually 6 times speed up on something like on average on the transpilation task on a single GPU machine running with Python 3.10. This was 3 years ago. And in fact, since then, they improved it even more, so they have now a 20% speed up on top of that. So the last case study is a compilation engine. So as I was saying before, compilation is a bit an overloaded word in quantum. You need to take an abstract language and bring it down to the level of pulses, but in the middle, you also need to do this program optimization. This has error mitigation, error control. So that's what a compilation engine does. And this team from Canada, Xanadu, decided to write a just-in-time compilation engine for programs that they already have in this language called PennyLane, which is basically one of these embedded DSL that are written in Python. So it's still something that you can use in Python by just decorating your circuits. The circuits is just a function for them, and then you can decorate the circuits with @QJIT, so quantum just-in-time. And just by doing that, behind the scene, it will be compiled in a just-in-time way, and you will have more efficient performance. These are some of the gains we tested ourselves. This was something I was building for them, some error mitigation stack, and we experienced that on a small toy example of 3 qubits, we have like 3 times the speed that without exactly the same code, but without decorating the circuits with just-in-time. So the stack here is more complicated, but so it goes through MLIR, if you are familiar with that, but the essence here is the same. You have a Python front end. You want to lower it down so that the core and the part where you need speed are written in something more performance than Python, which is C++. So, and in this case, the tracing is done by JAX. This is like more technical thing that you can look it up, but some binding to get back the function are in nanobind, which is sort of like PyBind 11, but slightly more efficient apparently. But yeah, the point is that the front end is still in Python, so you can write circuits in Python. Everything that happens behind the scenes, so sort of like the cool, interesting parts is in C++. So I'll skip the bonus slides because running a bit time. So what is the moral here? So I just showed you three case studies because I skipped the bonus one. One was a simulator, one is a transpiler, and one is a compilation engine, where that they are solving tasks that are really important for quantum software, but they are not quantum physics tasks. They are just classical tasks that we can solve with classical computational languages. So we used to solve them in Python in the beginning when we were writing prototype in this field. But now we are at the point where we need the speed in most of these tasks. So we are resourcing to languages that are more performant. So C++ is one of them. Rust is becoming one of them. And we want to keep the front end in Python for the reason I was saying before, for education, for rapid prototyping. And we just bind things with, between the performance language and Python with either C-type, PyO3, JAX, and nanobind. So this is at least the trend I observed, and I wanted to share this with you because maybe there is something we can do about it. Maybe the part that is really interesting, in my opinion, in quantum is this part where you need speed and performance. And I don't want to learn C++, I don't want to learn Rust. Can we stick to Python for these things? Going back to the survey, can we make sure that Python next year is, again, above Rust? Can we bring back, in other words, is like, can we bring back the quantum hot loops back to Python? So there are, in my opinion, some promising paths. This is mostly like an open question. It's something that I'm asking myself. I'm going to share it here. I'm doing some benchmarking and some prototyping. So maybe there is some hope. There is, the thing that we just saw, the compilation engine was using just-in-time, which is something that was introduced in just-in-time compilation, which is something that was introduced in Python 3.13. So maybe we can use the same techniques or use the very same compiler to do some of the quantum software compilation. We can do maybe better multi-threading, better parallel tasks, which are tasks like the one I showed you on transpilation on the graphs, or tasks like the simulation one where you needed the help of a GPU, Maybe we can start doing them in Python if Python becomes more efficient. There is I know there is an optional way to disable the GIL in Python 3.13. So maybe that's something to experiment with also for quantum tasks. CUDA by NVIDIA now has a native Python support since April 2025. There is a new language, Mojo, written by the same person who developed the MLIR stack, that promised to have some of the feature of Rust, but with the same syntax as Python. So maybe we can write a quantum computer simulator in Mojo, for example. So in my opinion, there are things we can do here. And yeah, that basically. Oh yeah, some notice that some of these things are experimental. I think the JIT is still like, there is still not much improvements, but in terms of benchmarks, but there is a bit of speed improvements. It's still in experimental mode. I think disabling the GIL is not really recommended, it's optional, but you can do it since Python 3.13. So yeah, I encourage people to experiment with those things when it comes to quantum computing tasks. That was the end of my talk, but I just want to plug two small things. So we are running a hackathon where you can actually get real money. You can go on unitaryhack.dev. There are 50 open source projects with bounties attached to it. You go there, solve them. Most of them are classical problems like the one I was talking about before. There are 800 hackers that signed up, and yeah, you can win things like $100 to solve a GitHub issue. There is also a real an event in real life in Milan on June 9, and also we are hiring a full stack web developer. Yeah, reach out to me if you're interested. Yeah, that was everything.